In February 1942, a Mexican farmer named Dionisio Pulido was working in his cornfield when he suddenly heard a sound like thunder. He assumed it was just a storm, but the reality was far more violent. A crack had opened in the earth, spitting out searing gas and jagged rocks. This was the sudden birth of the Paricutin volcano. For the next 9 years, Paricutin roared, eventually burying 200 square kilometers, an area roughly the size of a small city, under a blanket of lava and ash. It's one of those rare instances where humans actually witnessed a volcano emerge from the soil in real time. But what is the invisible tipping point that turns a stable piece of ground into a fountain of fire? Today, we're going to break down the 3 specific physical forces that determine if we're safe or in danger. Now, many geologists suggest the Paricutin event was driven by a precise sequence of gas bubble formation and movement, a mechanism that essentially transforms the subsurface into a high-pressure engine. To understand how a quiet cornfield can transform into a volcanic peak, we have to travel deep beneath our feet. Down there, we find the magma chamber, a massive reservoir of molten rock. In many regions, this liquid state is achieved when ocean water seeps into the Earth's mantle. It's not just that the water wets the rock, it actually lowers the melting point of the layer, a chemical shift that allows stone to liquefy at temperatures that would otherwise keep it solid. Now, consider the sheer weight of the crust pressing down on this chamber. It's a crushing, immense force. However, magma is less dense than the solid country rock surrounding it. Because of this density gap, buoyant forces push the magma upward, much like a bubble of air trapped in a vat of heavy syrup. An eruption occurs if this molten rock finds a structural weakness to exploit. Most of these chambers sit relatively close to the surface, typically between 1 and 10 kilometers deep. It's a strange irony that the very process that eventually cools a volcano can be the exact trigger that causes it to explode. To prevent a mass of liquid rock from bursting through the surface, the Earth maintains a massive, invisible stalemate. It's a 3-way struggle between lithostatic pressure, magmatic pressure, and the structural strength of the crustal rock. First, we have lithostatic pressure. Think of this as the colossal weight of the Earth's crust pressing down from above, acting as a heavy lid on a boiling pot. Opposing this is magmatic pressure, the internal outward push from the molten rock itself. But the stalemate isn't just a matter of opposing pressures. The structural integrity of the crustal rock provides a physical barrier, a reinforced wall that prevents the magma from simply punching through. This is essentially a problem of structural failure. While the magma is naturally buoyant, the system remains stable as long as these 3 forces are balanced. However, the moment this equilibrium is disrupted, the risk escalates. An increase in magmatic pressure is the most frequent catalyst. When the internal push finally outweighs both the crushing weight of the crust and the physical strength of the rock, the lid finally snaps. Think of a shaken soda bottle. The carbon dioxide is dissolved and invisible until the cap pops. Magma behaves in a remarkably similar fashion. As it rises and the pressure drops, it undergoes a process called vesiculation. This is where soluble compounds, primarily water and sulfur, transform into millions of tiny gas bubbles. These bubbles reduce the overall density of the magma, which in turn amplifies the buoyancy force driving it upward through the crust. Essentially, the liquid transforms into a frothy, expanding system, creating a massive amount of internal lift that fights against the weight of the rock above. This isn't a slow, steady climb. When the pressure hits a critical threshold, the result is explosive. When millions of these gas bubbles burst simultaneously, they generate a sudden, massive thrust. This is the force that catapults volcanic ash high into the stratosphere, far above the flight paths of commercial jets. It's a violent transition from a heavy, silent liquid to a pressurized, expanding gas, a process that turns a dormant chamber into a geological cannon. This specific mechanism is the engine behind the world's largest eruptions, including the supervolcanoes we'll examine shortly. Here is where the physics becomes counterintuitive. You'd assume that as magma cools, it becomes more stable and the danger fades. In reality, the opposite happens. As the magma cools and begins to harden, certain minerals crystallize. However, these crystals do not incorporate the dissolved gases. This means the gases become more concentrated in the remaining liquid. It's like a sponge being squeezed. As the minerals take up space and solidify, the dissolved gases are forced into a smaller and smaller volume of melt. This process, known as second boiling, and it's a bit of a paradox. The very act of the Earth cooling its own rock actually primes the pump for a catastrophic eruption. It's a paradox where the loss of heat leads to an increase in volatility. Sometimes the trigger doesn't come from a push from below, but rather a release from above. When a massive landslide removes huge volumes of rock from above a magma chamber, it causes a sudden drop in lithostatic pressure. Geologists call this unloading. It's effectively the same as ripping the lid off a pressure cooker. Consider the 1980 eruption of Mount St. Helens. The northern flank of the mountain essentially collapsed, removing the weight that had been holding the magma captive. Because that overhead weight vanished, the internal pressure became an overwhelming, unchecked force. This same phenomenon can occur more slowly through erosion or the melting of glaciers. Some researchers are now concerned that glacial melt caused by climate change could trigger increased volcanic activity. If the ice disappears, the reduction in weight leads to further unloading, potentially destabilizing the once solid structure of the crust. The Earth's balance is far more fragile than it appears. Beyond the pressure of gases, the Earth's foundations can simply disintegrate. This happens through hydrothermal alteration. Imagine the rock surrounding a magma chamber being chemically eaten away by acidic gases and extreme heat. Over time, this erosion turns hard, ancient igneous rock into soft, malleable clay. It's a sobering thought. The very bones of the Earth are softening, weakening the barrier that keeps the magma underground. Tectonic activity also accelerates this failure. Earthquakes can shatter the crust, carving out deep cracks, while continental plates moving apart can stretch and thin the rock layer. These fissures provide low-resistance paths, expressways essentially, for magma to reach the surface. When the structural strength of the crust fails, the pressure balance is shattered, and the molten rock no longer has a lid to hold it back. Let's shift our focus to a scale that makes standard volcanoes look like minor leaks in a dam. Take Mount Mazama in the Oregon Cascades. Over the last 400,000 years, it showed variable activity, but everything changed approximately 7,700 years ago. A climactic eruption occurred, ejecting 50 cubic kilometers of material. To put that in perspective, that is enough material to cover the entire city of London in a layer of ash hundreds of meters deep. This event was so violent that it didn't just blow the top off the mountain, it caused the entire summit to collapse, forming the crater lake caldera. How does the Earth hold back such a staggering volume of rock? Researchers modeled the interactions between the magma chamber and the surrounding dikes over 50,000 years preceding the eruption. They discovered that unsteady mantle melting triggered a massive growth episode. Specifically, there was a tenfold increase in deep magma influx before the caldera event. This created a massive oblate spheroidal chamber with an overpressure of 10 to 30 megapascals. Imagine the weight of thousands of meters of rock pressing down, while the magma pushes back with a force that eventually snaps the crust. This growing zone of influence causes regional vents to migrate away from the center. Once the chamber finally drains during the caldera-forming eruption, the activity returns to the center. It's a brutal cycle of accumulation, extreme pressure, and total collapse. It's a humbling realization that predicting these events remains incredibly difficult. We can calculate the crust's strength and weight with reasonable accuracy, but we're essentially blind to the real-time pressure changes inside the magma chamber. The extreme depth and heat make measuring magmatic pressure directly nearly impossible with our current technology. We understand the physics of the process, but we cannot see the gauge on the pressure valve until the valve is already breaking. Since we cannot physically enter a magma chamber, we rely on a high-tech digital eye. Volcanologists now employ thermal imaging to detect underground hotspots, mapping the heat signatures of moving magma. To understand the chemistry of the pressure, they use spectrometers to analyze the gases escaping from the vents, which serve as a chemical fingerprint of the subsurface. Finally, we track the physical swelling of the mountain. Precision lasers monitor the effect of rising magma on the volcano's shape, detecting deformations as small as a few millimeters, changes that are barely perceptible to the human eye, but signal a looming disaster. Our safety on this planet depends on a precarious, temporary equilibrium. On one side, we have the crushing weight of the world. On the other, we have the internal push of molten rock and the frantic expansion of gas bubbles, like a shaken soda bottle waiting for the cap to fail. From the 200 square kilometers of ash left by Paricutin to the 30 megapascals of overpressure that fuel supervolcanoes, the Earth is constantly calculating a balance of strength versus pressure. We live on a thin, cracking crust that acts as a fragile lid for a global engine of fire. The question that remains is not whether the balance will shift, but where the next structural failure will occur, and the weather will detect the swelling of the ground before the lid finally snaps.